Hello, and welcome back. I'm Matthew Lay, and in today's lesson, we are going to study the first combination circuit, which is called the parallel series circuit. In this lesson, we've got some objectives. First, we want to name two types of circuits, two combination circuits that could be made using three resistors. Then one of them is going to be a parallel series circuit. We want to define that. And then we want to list the steps for solving a parallel series combination circuit. So let's get started. Okay, so when we talk about construction, if we add one more component, a third resistor, how many different configurations can we make? Now there's a couple that we've already studied. One is a series circuit, which looks like that. So we could have three resistors in series. Another is a parallel circuit. And a parallel circuit, a pure parallel circuit would look like this. And all three resistors would be in parallel with one another. When we get to these combination circuits, there are two other configurations we can make with three components. The first one is called a parallel series circuit, and this is the parallel series circuit, which it looks like a parallel circuit except in at least one of the branches. In this case, it would be only one of the branches because we have three components. There is a series connected set of components. So here in CD, we have two resistors that are in series, but that is a branch in a major parallel circuit. And then finally, we're going to study this one in another presentation, is the series parallel circuit. And that would be a series circuit that instead of having three resistors in series, it has one resistor in series with two that are in parallel. And that is a different circuit from the one that we were just looking at because this resistor right here is going to have total current going through it. Where if we go back here and look here, none of these resistors are going to have total current going through it. So we're going to find out that's a characteristic of a parallel series circuit and conversely, a series parallel circuit. Okay, so that is our series parallel circuit. We'll study that next. So the parallel series circuit. Let's give a good definition for this. A circuit whose major components are parallel in configuration, and they have minor branches that contain components that are connected in series. Okay, so this is our schematic for that. Okay, so we have a major parallel circuit, meaning that each branch has total voltage across it, and one branch is just comprised of one resistor. The second branch is comprised of two resistors connected in series. Okay, so that is our parallel series circuit. And of course, you can have a parallel series circuit with more than three resistors, but this is the simplest form of a parallel series circuit. A defining characteristic of a parallel series circuit is no component in the circuit shall have total current flowing through it. You see, right here at point A or node A, the total current is going to be divided. Okay, that's Kirchhoff's current law, that the sum of the current coming into that point has to equal the sum of the current coming out. Well, we know that some of it is going to go this way and some of it's going to go that way. So we do have a current divider, and since this circuit is a current divider, it is going to be a parallel series circuit. We do have current flowing that way and that way, and neither one of those two will be total current. Total current will actually be the sum of those two currents. Okay. Now to solve this thing, we are going to just break it down into two little individual series circuits. And then we're going to treat those individual series circuits as if they're in parallel because they are actually in parallel with one another. And then we're going to solve all those branch configurations from our total. Okay, so we're going to walk through an example here. Here is a parallel series circuit, and I have a given of 25 volts, 880 ohms for R1, 1K for R2, and 500 ohms for R3. Okay, so first we want to solve for branch 2. So you can do this literally when you're working on your worksheet. Just cover up branch 1 with your finger. And what do we have then? We have a series circuit. We literally have a 2 resistor series circuit with a power supply, okay? So we're just going to use that characteristics that we learned in our series circuit to solve this portion of the problem. The best way to solve any of these is to break the problem down into smaller components and use the characteristics you've already learned and then build out from there, okay? So here, to get the branch resistance of RCD, remember, RCD is just from here to here. All we have to do, remember, in a series circuit, resistance is additive. So we're just going to add the 2 resistors together, R2 plus R3, and that's these 2 givens down here. So 880 ohms plus 1K ohm. I take that back. It's 1K ohm plus the 500 ohm. So that's why it's 1.5K ohm there. Okay, so that is my branch resistance. Okay, so now we know the branch resistance. We can use our Ohm's law to figure out the current. We know that because that branch has the total voltage across it, we're going to use total voltage divided by that branch resistance, and we're going to get a branch current of 16.667 milliamps going through that branch. Okay. So now we can solve for branch 2. So we actually just now want to either imagine in our mind or just write on your worksheet, just cover up branch 2 with your finger. And what do we have? We have the simplest circuit you could have. Treat it like a series circuit of one component, and we're going to solve for branch AB now. So we want to get the current through there. We don't have to get we don't have to solve for the branch resistance because it's only one resistor. So we're going to use our total voltage divided by our branch resistance, 25 volts divided by our 880 ohms, and that's going to equal 28.409 milliamps. Okay. And then working on our worksheet, we're just going to go ahead and start filling these out. So the numbers that aren't highlighted here are just our givens, the 25, 880, 1K, and 500 ohms, okay? And then the ones highlighted in yellow are the ones we just solved for, okay? So this was the current through branch 2, and since it's a series circuit, current is common, so that same current goes through both of those resistors. But now that we have combination circuits, we're not always going to have the same current here because this is a separate branch, and that branch has a different current going through it because it has a different resistance across it. And we know that that branch has 25 volts across it. Now here, remember, these are in series with one another. You can see that here. They're in series with one another. And what is a series circuit? It is a voltage divider. So that 25 volts is going to be divided up amongst those two. Okay, so we're going to solve for that next here. Okay, so we want to solve for the voltage drops in branch 2. And so again, we're going to cover up branch 1. We're just going to pretend like this is a series circuit. We know that the current through that is 16.667 milliamps. And we know the resistance of R2, it's a given, is 1K ohm. So we're just going to take our 16.667 milliamps times our 1K ohm, and we're going to get 16.667 volts. Okay, so that's going to be our voltage drop. That's going to be across just this resistor right here. Okay, now we can do the same formula, just substitute E3 and R3 in the formula, and it is going to equal 8.33. I believe I show you the formula here. Show you the equation. So 16.667 times our 500 ohms, and it's 8.333. Since 500 ohms is half of 1K ohm, it makes sense that the voltage drop is going to be 1/2 of the voltage drop across R2. Now, if you look, you can see that these two are going to add up to 25 volts, and that is our source voltage here. Okay, so we're going to go ahead and fill those in to our table here. So these highlighted yellow areas are the ones that we just calculated. And you can see the dominoes really start falling now. We can go a number of different directions here. Notice now, because we're dealing with combination circuits, we can't add up all these numbers and come up with 25 volts. This one is a cross source voltage, so it is 25 volts. These two should add up to 25 volts, but we can't add every line here anymore because we don't have a simple series circuit to be able to do that. Okay, so now let's solve for total current. We know the currents through each branch. We know IAB and ICD, so we're going to add those two together to get our total current. And so we have the 28.409 and the 16.667 milliamps. We add those together and we get 45.076 milliamps. So that's our total current. We're going to go ahead and fill that in here. And then we can go a number of different directions, but we're going to go ahead and calculate our total resistance next. So let's get our total resistance. Our total, this is just Ohm's law, equals our E total divided by the I total that we just figured out there. So our 25 volts divided by the 45.076 milliamps, and we get 554.609 ohms of total resistance. So we go ahead and fill that in our table here. And now here we're just going ahead and it could be your choice as to how you actually want to calculate power, if you want to use I squared R or I times E. So we want to solve for all the powers just using our Ohm's wheel. And as I've stated before, I kind of like to use the givens. So since we are giving voltage and resistance, I went ahead and used our 25 volts squared divided by our resistance. And our AB is 880 ohms because we only have that one resistor in there, and we get 710.227 milliwatts for that particular branch. And just to show a couple of different ways, I'm going to use a different formula for the power on R2. Now I couldn't use E total there, right? Because I don't have total voltage drop across that resistor because it's in series with another resistor in that branch. So I did have to use the total current. I could have actually used the voltage drop across there divided by R2, but I decided to use current instead. And so the 16.667 milliamps squared times the 1 k ohm equals 277.789 milliwatts. Okay. Going to use that same formula for the other component in that branch, and 16.667 milliamps squared times the 500 ohms is going to be half of the power that we had above there, 138.894 milliwatts. Okay, and then to get total power, this is true in series circuits, parallel circuits, and combination circuits. Total power is additive. So we can just add up all these powers, and when we sum all those numbers together, we're going to get 1.127 watts. We can check ourselves by just taking our total current and multiplying it times our total power, and it gets the exact same value. So that's a quick check you could do. If it doesn't come out, those two, then you've got a problem somewhere in your calculations. So that's just very, very handy to do. Then I just filled in all of our powers here to round out our table. Okay, so let's review. Name the two types of circuits that can be made using 3 resistors. So if you want to pause the video and then come back. Okay, we can make a parallel series circuit, which is what we're studying in this lesson, or we can make a series parallel circuit, okay, which will be the next lesson. Okay, define a parallel series combination circuit. Again, pause the video, think about it, maybe write it down on a piece of paper, and then come back. Okay, a parallel series combination circuit is one whose major circuit has a parallel configuration with minor branch circuits or circuits that contain components that are connected in series. The major characteristic of a parallel series is total current does not flow through any one of those components that's in the circuit. Okay. And then list the steps for solving the parallel series combination circuit. And again, if you want to pause the video. Okay, first we want to solve the branches. So you want to get the branch resistance and currents first. Then you can calculate your total resistance and total currents, and then you can go back and get your individual voltage drops and the power dissipated by the circuit. So this concludes our lesson on parallel series circuits. I hope that was helpful, and we'll see you in the next lesson.